All right. So, actually, we went through a lot of probability laws. Tables last class. So basically today, I'm going to show you how we would build our own contingency table. All right. So before I was just giving you these numbers, like where did they come from? Not really sure. I kind of alluded to at the end of last class. If we have a data set with frequencies, we can essentially turn those into probabilities by dividing by the total number of observations, right? Our probabilities are like relative frequencies. So I believe, oops, I put up two files and I'll show you them in a second. I forgot that I didn't open them up here today. Maybe let's open them up from Canvas so I can show you where they're at. So we'll go to files, we'll go to in-class data. And which one do I want to do? I think let's do the union data. If we have time, I'll show you the other one. I think this one's a little bit more, will be a little more beneficial for the next Excel assignment, which I have started to, so I did the other section first and graded them. So this maybe pertains a little bit more to them than to you. But I've got a couple comments. So one, the purpose of those Excel homeworks is that you're doing the work in Excel. So if I can't see the formulas and I just see numbers, I'm going to assume you copy and paste it, right? I mean, otherwise I have no idea to know if you actually did the work, right? So make sure that I can see your formulas. So I was pretty lenient, a little more lenient on this first one. I kind of left comments if that was the case, especially for somewhere I could see some of the formulas, not the others. But moving forward, I need to see all of your work in Excel. Two, I don't mind if you somehow find some of my old assignments and use them as templates. But when you're submitting data that wasn't put on Canvas, I'm a little suspicious, like I can't give you any credit. You didn't answer any of the right questions, right? Even if they look similar, I usually change years. I might give more observations or fewer observations. I might, I'm changing things up. I'm not lazy, right? And so be very aware that what you're uploading. I don't care if you use old stuff as a template or as a help, right? But, you upload the wrong file, or think that you can just, the first homework last semester is the same as the first one this semester, you're going to end up getting a pretty low grade. Okay. So that's what I have to say about that. With that in mind, we're going to be kind of moving into the next what would look like the next Excel assignment. Okay. Also, I had some people kind of ask me, like, how am I supposed to know how to do this or that? It's anything I ask you to do on any of the homeworks will be something we have done in class. I'm only going to expect you to know how to do things in Excel that I've shown you in class. Okay. So if you're Googling things and you're finding stuff that doesn't look familiar at all, well, it probably doesn't mean you shouldn't be using that, right? I'm showing you how we would do it, or everything, all the tools you would need in class. So for today, we're going to see how do we build contingency tables and then use those contingency tables to answer questions about different probabilities. Okay. So I don't know, I downloaded this data. It's got a bunch of different industries. It's got the percent of those industries that were union. It's got the union member weekly earnings, and it has non-union member weekly earnings. And then it also kind of created this difference, right? So just the difference between union, non-union wages there. So the idea is, if I can unionize, it gives the workers a little bit more power. Usually they can bargain for higher wages. And so if we see an industry that has a higher percentage of their workers unionized, we would expect that union has more power and that the difference in union versus non-union wages would grow, right? So that's what we're going to try to investigate here. And then I've got another example that, like I said, if we have time, I'll kind of work through. It's like drug use and I think intellectual ability or something. So here, just as kind of a refresher and also kind of a place to start, I'm going to figure out what this mean union membership is. All right, so that's just using the average function, then going over control shift, right, from the first observation, hold control and shift, or command shift on Mac, hit the down arrow. So I've got on average, it's about 10.7%. Now I could do the rest of these, relatively quickly as well. So here, I think this was union member earnings. And then, I've got them all in a row. So actually, got non-union, and then average,
So we'll go Control Shift, hit the down arrow. I've got my 4 means pretty quickly. Okay.
So using that average, which I found is kind of my place to start. So I looked at this and I was like, you know, the average difference in union non-union earnings is about $118. The mean is kind of like 10.7%. So I'm going to choose some cutoffs that are kind of close to the mean, close to this middle part of the data. But I'll show you that we could use other values as well, right? So I'm going to put my cutoffs up here. Instead of typing them every time, I'm going to use cell references so that if I want to go back in and change them later, I could, right? I could just change what the cutoff was and my tables would update. Okay? So I'm going to choose $100 as my cutoff for the wage differential. And then I'm going to choose 10% as kind of my cutoff for union membership. Okay? So I'm going to define things like just like we had before with our contingency table. I've got events A and A complement and B complement. And so how have I done this? Well, I've said, look, A is if the wage differential is $100 or more, so greater than or equal to 100. The complement of that is if the wage differential less than 100, right? And then for the event B, I said, is union membership 10% or higher? The complement was it less than 10%. Right? So we're going to be able to essentially, what we're going to do is go through, if I was to do this by hand, go through and count the number of observations, the number of industry year combinations I have, where the wage differential in that industry was $100 or greater, but also only count it if it had a union membership of 10% or higher, right? So I'll just go through the data and figure out how many observations meet that criteria, write that number down. I'll then go through how many of those industries had $100 or more wage differential, if I had below 10% union membership, and then write that number down. So I can't do this by hand, but I don't want to do that by hand, right? Especially with large data sets. So what can we use? Well, this is what you should have been using for part of that first assignment. I said that we're going to use it later on as well. And that when we were looking at the histogram, it kind of seemed weird that we like selected the same variable twice. Why don't I have to just select it once? Well, that's because the count ifs has multiple other uses, and here's one of them, right? So we're going to use that count ifs, and it's okay. What's the first variable you want me to look through? Well, I've got this union membership variable over here, right, in column C. So I'm going to select that. Now, once again, if you're on a laptop, you can go up here and type in the formula bar, but just for the sake of being able to see it a little bit better, I'm going to scroll up here. Right? And actually, if I ever forget and you can't see anything, remind me. Sometimes it's easier if I blow this up so you guys can see what I'm actually doing, right? So count ifs, we'll go over, select our union membership variable, then scroll back up here so we can see what I'm doing. Move this out of the way. Oops, maybe. There we go. Put a comma, right? So we selected that first variable. We want Excel to go through every single one of those observations and only count it if it's, I think this first one I had set up was greater than or equal to, right? So anytime we have these equalities in our count ifs, we have to put them in quotation marks here. We then use an and sign, so we can use a cell reference, and we want to know, is that union membership greater than or equal to that 10%, right? That cutoff that we put up here in the cell. Okay. Everybody with me so far? Questions? Okay. I'll then put a comma. Now, unlike when we were using this to do the histogram, well, now the second criteria I want to know, is that wage differential $100 or more? So now I only want to count the observation if I'm looking through another variable, which is this difference in earnings. So I'll select that, right? Scroll over, scroll back up so we can see what I'm doing here. Comma. Now, when I look through that variable, I only want to count the observation if that wage differential was greater than or equal to 100, right? Or $100 or more. So there I'll do what? Greater than or equal to, actually, I forgot something. Greater than or equal to in quotation marks. Then put an and sign, and I've got my $100 cutoff up here. Okay. So what this will do is it'll go through every observation, look first at that union membership variable, only count the observations if that's greater than or equal to 10%. Then go through the observations again, but now looking at that wage differential variable, count it only if it's greater than or equal to 100. Right? So this is going to give me every industry that has 10% union membership or higher and a wage differential between union and non-union members of $100 or more. Okay. So I hit enter, and sure enough, it does that. Okay. So these other combinations, right? These other top 4 left cells, remember they all represent intersections. It's count the number of industries where this and this are true, right? So I'm going to set up the other 4 top left cells a very similar way, right? I can use that count ifs formula. It's just that I have like different kind of events, right? Sometimes instead of greater than $100, I wanted less than, right? Or vice versa with the union membership. So I'll show you kind of a nice quick shortcut, which is I'm going to hit F4 or Command T on a Mac after selecting the cell references for where the data was at. Because I never want that to change. I always want to keep looking through the same cells. Now, in this instance, actually, my cutoffs are going to stay the same as well because of the way I define my complements. So I'm actually going to go ahead and freeze every single cell reference here because I want to just copy this over and then just change my equality signs to match up with my other events, right? The complements and things like that. Okay. So I froze everything, right? Hit enter. I'm going to drag this over and drag this down. Hopefully, if I froze everything, right, that number is exactly what it was, the same, right? It doesn't change at all. Right? Another way of doing this, just to be fully transparent. There we go. If I didn't freeze those cells and I wanted to copy it over, if I click, like double click, left click, it'll select everything that's in that cell for me. I can also copy, hit enter to get out of the cell. Then if I click in this cell and then paste, notice if I copy and paste this way, it doesn't update cell references. So I could do that. I could like go in and copy and paste. To me, that's a little bit more cumbersome than just freeze everything, drag it over and drag it down. But that is another way you can copy and paste without updating the cell references as opposed to freezing them, right? But I kind of prefer freezing them. I think if I do this, yeah, it doesn't like that. It's kind of annoying. Can't select it all at once, but that's how Excel works for whatever reason. So I'm going to use the dollar signs because I just think it's a little bit better practice. And now I'm going to go in and just update that count ifs formula to match up with these different kind of row and column headings. So this one, I want to count the number of observations that are below 10% union membership and $100 or more wage differential. Okay. So remember, the first thing that we were looking at was that union membership. Well, instead of being greater than or equal to, I now only want to count it if it's less than, right? But I still want to know, is that wage differential greater than or equal to 100? Okay. So I just have that same count ifs formula, is going and changing the equalities, okay? Go down to this cell. This time I want to count it if it's greater than or equal to 10%. Okay, union membership, that's right. But on my second variable now, I only want to count it if it's less than $100, right? So I change that sign to match up with that kind of row label. I then go in to this last one. Here I want it to be below 10%. So I change this to be a less than sign, and then also less than $100 more wage differential, right? So I've got the same count ifs formula. I'm just kind of changing what my equality or inequality signs are there. Once I do this, I've now got my frequencies for each of these different combinations, right? A and B and A complement, B complement. So one thing I'll point out here, it becomes really important that notice when I'm looking at being less than 10%, I keep it strictly less than. And then here I've got 10% or higher. So I only have the equality on one of those, right? Because in order for it to be an event and its complement, I can't have any value that would be counted in bold, right? An event and its complement we can think about are mutually exclusive. There should be no outcome that's in both of those, right? So be careful with your equalities in other examples if we're working on this, okay? Any questions or want to see one of the cells again? Or keep moving here.
Yeah, can I see the 221 zone again?
This one?
Mine's pulling up at 0.
So what might you, what's an error you might be using? If you had, are you using the right cutoff cell references? So did you select column C?
Yes. Operators.
And then did you select column H for the second one?
Yes.
Okay. And then when you're using your criteria, are you selecting the cells where you put 110 in there? You might have them reversed. So one thing, be careful. I'm thinking maybe like, if you accidentally used 100 as your cutoff for union membership, nobody's going to have greater than 100% union membership.
Okay.
So you might have flipped those. Yeah. Okay. Okay. So sometimes I can troubleshoot without even seeing it. But all right. So we've got these frequencies, which kind of represent the intersections. Okay. We then, just like we could with probabilities, how could I recreate those total columns? Or those. What did we say we do in tables when we have probabilities? To get those totals, I simply add across the rows and down the columns, right? And the reason why is because think about it. Here, if I want to know how many of these industries have a wage differential of $100 or more, well, if I take every industry that had $100 more wage differential, but 10% or higher union membership, add to that every industry that had $100 or more wage differential, but less than 10%. Well, that would count every single industry that had a wage differential of $100 or more. So I can add it across these rows to reproduce my totals and then down the columns as well. Similar idea. So what function can I use in Excel for that? Pretty quickly, just that sum function, right? Select these two, oops, all right? I'm gonna just add across the rows. I can then copy this down. I could go over here, add down the columns, right? Drag that over, right? And now I've got the frequencies that are kind of underlying or laying behind the scenes for my contingency or my probability table. So what should this number represent? 735. Yeah.
All of the data.
Should be the total number of observations. So what's a function we said we can always check to make sure that, you know, if we know something should be the total number of observations, if I use that count function and I just count one of my variables, I'll go back up here. Hopefully I get the same number I did down here in this bottom right corner of my contingency table, right? That's a good way to kind of know, like, oh, at least I'm on the right track. I'm not making egregious errors, right? Other questions? You want to see us? Yeah.
The dollar signs are supposed to be for all the.
Yep.
Reference, right?
Yep. Just freeze everything. Yep. And then we just change those equalities. Well, you know, less than, greater than. Yeah.
Is it possible to just highlight the whole thing?
So it's not. So for instance, you can actually do other crazy things with cell references. So notice I'm hitting F4. It's not doing anything. And that's because in between my cell references, and it has something that's not a cell reference. So I can select consecutive cell references as long as there's no other characters in between. And for these ones, right, I can hit F4 and it actually puts the dollar signs in there for me. But yeah, unfortunately, with a function like this, if I highlight across something that's not a cell reference, it won't. I don't know why it's programmed to be that way, because I know that you can program it to register those as characters as opposed to cell references, but here we are. I didn't make Excel. Right, so, any other questions? Okay, so to then go from our frequencies to building an actual contingency table, it's really simple. Like, don't overthink it. If I know the number of industries that have $100 or more wage differential and have 10% union membership or higher, there's 221 of them. Out of the 735 different industry year combinations I have, then empirically, to assign that probability, I would just take
221 divided by 735, right? 221 of the 735 industries were in this kind of met this criteria. So all I'm going to do, take the frequency for that kind of combination of events, A and B here, or 10% or higher, $100 or more, and then divide that by my total number of observations. Now, when I copy this over, it's going to update from K9 to be what, L9, K10, L10, right? And it's just going to be kind of grabbing the different frequencies that match up with these different combinations of A, B complement, B, A complement, and these other four cells or other cells in my contingency table. Now, the problem is if I copy this over and down, what also updates my number of observations, right? Or that kind of total there in the bottom. So I need to make sure I freeze that cell reference. Okay. So now when I copy this over and then down, it should be updating these cell references to always kind of just take the frequency for whatever that cell represented, divided by the total number of observations. If I've done it correctly, well, then when I get to that bottom right corner of my contingency table, hopefully this is 1. Okay? If I take every single industry that has $100 more wage differential and every single industry that has less than $100, well, that covers everything, right? Those should add up to 1. Okay. Any questions on that before we keep moving? I'm trying to walk through it slow so you can kind of follow along. Is there anything else I want to say here? I think that should be all right. So here's where on your next Excel assignment, like that's the portion that you're going to have to do in Excel, right? I might then ask you some questions that you can, do in Excel, but it's also things that we could be expected to do by hand, right? It's just a little bit easier in Excel because instead of typing numbers in my calculator, I can just click on where the values are at, right? And I'm not constrained to like 2, 3, 4 decimals. So for instance, if I want the probability that I've got union membership of 10% or higher here, what cell represents that? If I want the probability of having 10% or more union membership, just go down to my total count, or total row, sorry, 0.39. Well, instead of typing in 0.39, well, and worrying about, well, what decimal do I round it to? Just put an equal sign and select this up here, right? Now I hit enter, just got that value. The next one, what's the probability that I get what, 10% or higher, and the wage differential is $100 or more? Well, which cell should that be there? What value, roughly?
It's gonna be the 0.55102.
So be careful, right? I don't just want the probability of having a wage differential of $100 or more. I want it to be 10% or higher and wage differential of $100. Right, so I'm just going to go 10% or higher and $100 or more. So I have those top 4 left cells representing intersections. So this guy right there. Got a slightly, well, actually, I think I left one off here. So I'm going to add one in. Let's say I wanted the probability of being below 10% or wage differential of less than $100. So there you've got the probability of an event, probability of an intersection. Those are kind of easy. Those are just one number from our contingency table. We said if we wanted the union, so A or B, or this event or this other event, what did we have to do? Well, in general, the union of 2 events we could write as add up each event, but then subtract out what we double counted, right? What was in the intersection. So for us here, our 2 events are being below, and actually I'm going to widen this so we can kind of, there we go. Being below 10%. So that's my first event. I would go down here. That's the probability of being below 10%, right? Or my first kind of event that I'm interested in. Then I want to find the probability of my second event, which is having a wage differential of less than $100. So add to that the probability that I see a wage differential of less than $100.
And then the final thing is I need to subtract out the intersection of the two. So if I want being below 10% and having a wage differential of less than $100, that should be this 0.357 cell, right? So I'll subtract that intersection. So all I'm doing there is taking that kind of addition rule that we looked at and applying it in Excel, right? Just having Excel do that calculation for me, finding the union of two events by adding the probability of each event and then just subtracting out that intersection. Okay. Now I said there was also another way of doing this. I could have, this is like the non-technical way. I said, if you ever want the union of two events, just go to its intersection, make an L, and if you add those up, it'll actually give you the union, right? So just to kind of prove that I'm not making that up. And I kind of gave you a visual representation as to why, right? We should get the same thing, right? So you can do it kind of either way here, right? I think the first way kind of matches up more with like what the technical kind of way to do it is. So I generally try to, prefer that, but you can do it the other way as well. Any questions on that? You want to see one of those cells again? Yeah.
Did you post the attendance today?
No, I haven't pulled it up yet. I'll probably do it at the end just to kind of give you guys credit for being here, but I'm trying to finish up this first. No, you're good. So we've now got the union. We can also do something like find conditional probabilities. Okay. So here I want to know, okay, if I condition on the fact that the industry has 10% union membership or higher. So of just those industries, it's like I now went from every single observation to only the industries that have 10% union membership or higher. Now what's the likelihood or what's the probability that they have a wage differential of $100 or more? So we said for that, if I wanted a conditional probability, that's going to be the intersection of whatever those two events are. And then we've limited the space, experimental outcome space, it was 1. Now we've limited it down to whatever the probability of that event that we have conditioned on is, or whatever that event on the right-hand side of my vertical line is. Okay. So here I've got, okay, I want this conditional probability. It should just be the intersection of these two events. So the probability of $100 or more or 10% union membership or higher. So that would be up here, right? And then divide that by whatever I've conditioned on. All right. So what I've conditioned on here is that the industry has 10% union membership or higher. Right? So I go up here, 10%, 10% union membership or higher, and I select that. Right? Hit enter. Now I've got my conditional probability. Okay. So one thing I wanted to point out, or I want to point out here is, can I say that these events are independent? Right? So I might have to scroll up a little bit so you can see the titles here. But how would I check to see if these events are independent? Remember what the definition of independent was. So I said two events are independent if the unconditional probability of that event is the exact same as the conditional probability. Well, I now have the conditional probability. Whoops. So all I want to do is see, is that the same as the probability of the event itself? So if I just wanted the probability of being $100 or more wage differential, that would be up here. I can see those two things are not the same. So if they're not equal to each other, we would say these are not independent events, right? And it kind of makes sense here. Like if I just chose an industry at random, the likelihood that the union non-union membership is $100 or a wage difference of $100 or more is about 55%, right? But if you tell me, well, look, given that you're looking at an industry, so I've chosen one at random, but I'm telling you with fact that it's a guarantee, it has 10% union membership or higher. So I know it's one of these industries that has pretty high union membership. Well, then that union has more power. It should be that likelihood they can get $100 or more wage differential is even greater. Sure enough, once I conditioned on the fact that it had union membership 10% or higher, my conditional probably went from what, 55% up to about 77%. Right. So we can start to answer like relevant questions, even with a very simple contingency table here. Right. If I'm a company in one of these industries, I might look at this and say, well, I want to keep wages low.
I might really want to fight the unions, right? Because otherwise I'm going to have to pay much significantly higher wages. Okay. So we can do other conditional probabilities as well. So just to kind of get some more practice, if I want to know what's the probability, I see $100 more wage differential, given that the union membership is below 10%. Well, now it's the same kind of setup, right? I want the conditional probability. So that's going to be the intersection of these two events. So $100 or more wage differential and below 10%. But then I'll divide that by, if I can show you this here, there we go. Whatever I've conditioned on, whatever event I've conditioned on. Well, here I conditioned on being below 10%. So I go up here, the probability of being below 10% was in that cell. And now this should give me my other conditional probability, right? Well, I can see here, if you give me the information that the industry has low union membership, right, below 10%, well, now the probability that I can get a wage differential of $100 or more between union and non-union members, instead of whatever it was, I think 55%, now it's fallen to 41, right? So in a lot of cases, things are often dependent on each other, right? Having this additional information about the industry will kind of change the probability of whether or not the wage differential was greater. Any questions on that? I want to see one of those cells again. Okay with that? Yeah.
Why was the first
Here?
no, sorry, the one we just did.
This one? Or this one?
Yeah, that one. I just don't know why it was different on the below 10% and the above 10%.
Yeah, so if you think about it, if I tell you, like what we're doing with the conditional probability is almost like I chose one of these industries at random. You can't see it, I can, and I'm telling you that it's an industry that has 10% union membership or higher. What I'm not telling you is not, this is like a thought experiment, right? But what I'm not telling you is that the wage differential is $100 more. What would that probably be? Well, once I tell you that you know it's one of these industries that are 10% union membership or higher, my entire experimental outcome space is no longer 1. It's only 0.39. And of that remaining 0.39, how many of the industries have $100 more wage differential? 0.3 of them. So 0.3 over 0.39 would give me kind of this new conditional probability. And then the other one I was conditioning on having below 10%. So now instead of the entire experimental outcome space of 1, I've got 0.6. Of that remaining 0.6, you can kind of see here, 0.25 of it is $100 or more. You kind of see this is really imbalanced, right? This one we have the wage differential of $100 or more being less than the wage differential of $100, and this one, right, 0.3 versus 0.09, a much larger percent of that space is going to be kind of filled up with industries that have $100 or more wage differential. Does that kind of get at your question? Yeah. Any other questions on this before we keep moving? Okay. So we'll go up here and I'll kind of show you something that I think is kind of neat, right? So I chose numbers that were kind of close to the mean. Sometimes that doesn't produce that interesting results because like there's 50% on either side. And so, you know, we see with our frequency, you know, these ones are kind of close. Yeah, these ones are all split up. So what I'm going to do is like choose an even higher cutoff, right? Maybe I want to say, okay, I'm actually going to only define high union membership as 15% or higher. Now, my labels won't update, right? But my table will, right? So maybe if I had kept my label a little more general where I said high union membership, low union membership, and then I just knew I was using this cutoff value up here, then the table would still make a little more sense, right? I don't have to go in and change my labels. But that's probably a little bit trickier for you right now. Kind of having that label up there is going to be beneficial. But in practice, like if I was doing this for some project down the road, maybe keep it more general so I can go in, change these cutoffs, all my frequencies update, all of my probabilities updated, and all of my work here for these unions, intersections, everything updates, right? So if I use cell references and I put my cutoff values up here, well, then I can play around with, well, what about $150 or more wage differential? Everything updates, right? I get my new probabilities. Okay. So, you know, I think hopefully what we're starting to see, if I have larger projects where I'm doing a lot of work based off this same source data,
cell references can save us a lot of time. Can you imagine, instead of using those cell references, I type 10 and 100 every time, and then I have to go back in and change every single thing, just really time consuming, right? So that's the real power of cell references. And honestly, it's easier to click on a cell than it is to type in 100 or 10 anyway. So we want to always try to rely on those cell references. So I saw a couple of assignments that I graded, you know, they didn't use the count ifs. Instead of setting up that minimum maximum bin, you typed in every single number. That's fine. But I'm trying to, you know, show you things that make it so those assignments, you know, wouldn't take as long if you don't have to sit there and then kind of type every single number in. Like we can exploit these cell references. Any questions over anything here? You want to see something again? So I'll just pull it up. We won't work through it. So I thought this was kind of interesting. It's also very business related. There's some discussion of, you know, we're in a business college. Some people don't like when we do non-business related examples, although my argument would be everything can be, you know, everything's a product, right? So, you know, this one I think looks a little bit less businessy, but it's kind of interesting. And it's just another example if you're going to, once I put that next homework assignment up. So I had this huge survey data, and I had like drug use, and then I had this thing, which was the ASVAB. It's like a test. I think they make, I don't know if you saw take it in the military or not, but they use it to kind of get an idea of like what it's like an IQ measure, right? Kind of how it's supposed to represent intelligence, right? So I kind of set this up to where you could do something like, were they above or below the 50th percentile, right? And then here was, have they ever used cocaine or not, right? So this is just a 1-0. So, you know, the one that we just worked through, I think it was a little bit easier to think about, like we had this greater than or equal to or less than. Sometimes we can have this example where if I'm just saying, is it equal to 1 or 0, right? Because sometimes we'll have variables like this, where was it? Well, I thought I had it in here. How am I doing this? Cell N and P. Oh, because these numbers represent weird things. That's why. Okay. So yeah, we could kind of just use that 1-0 variables too. Like if I just had, did they use cocaine or not? So here's just another example. It's the exact same stuff that we just did. I'm just using different cutoff values, right? And my events are defined a little bit differently, right? I then kind of did a very similar thing where I then turned those frequencies into probabilities, right? All I did there was simply divide each frequency by the total number of observations, right? I did kind of something similar for marijuana use, just to kind of, I don't know, have some additional examples. You could then answer questions based off this, just like we did, right? What's the intersection of these two events? What's the union? What are the conditional probabilities? Check for independence, okay? So just another example. It's up there on Canvas if you wanted to kind of play around with it. I'm not going to sit and work through the whole thing in class, but just I had it sitting there. I might as well give you two examples as opposed to one. Yeah. Yeah. So I'm kind of showing you, like on the homework assignment, I'll give you what these values should be. I'm kind of showing you in practice, like generally look for like what the mean is, and then get an idea about like, okay, what would be, you know, high cocaine usage, or what would be kind of a high ASVAB score, things like that. So in practice, it just depends on the question you have, like what those cutoffs will be. On the assignment, I'll give you what those cutoffs will be. Any other questions? Excel stuff before we keep going. All right, so let's try to finish up these slides today. So let me pull this up so I can give people credit here, since I forgot to do it ahead of class. I've got enough things open. So the rest of the class should go pretty quick. I've got some what I think are interesting examples that we'll kind of work through once I get this pulled up. So one thing that I mentioned earlier was this idea of independence. Right? So we said if two events are independent, oops. One thing that we can do is calculate the intersection a little bit differently, which is
the intersection of two independent events should just be the probability of each event multiplied by itself. Okay? So this idea of independence pops up a lot in the real world. So if you think about like flipping a coin, you know, what's the probability it comes up heads on your first coin flip? 0.5. Well, let's say you see like 5 heads in a row. What's the probability that on the 6th coin flip you get a heads? Still going to be 0.5, right? So this is the idea that coin flips are independent. So I can start to play around with things like, and here I already answered this question, but right, if I see like 5 or 6 tails come up in a row, is it, you know, more likely to see a heads? No, every flip is independent, right? But a lot of people fall victim to this, what we call the gambler's fallacy, right? If I know that flipping a coin, 50% of the time it comes up heads, 50% of the time it's tails. Well, if I see 5 tails in a row, I think, oh, well, it's got to balance out, right? So I have to start seeing more heads. Well, not necessarily. Every single flip is independent, right? And so you see a lot of people fall victim to this gambler's fallacy when we have independent events, which is why it's important to check for independence, right? Because we don't want to be falling victim to this. In fact, I kind of like did a simulation. You can recreate some random number generation itself, and you kind of see following a coin flip that was a tail, the next coin flip, you know, heads about 50% of the time. Now these are a little off because I only did it 10,000 instead of an infinite number of times, right? After 2 tails in a row, the probability that it came up heads was barely below 0.5. 3 tails in a row, the probability that it came up heads is just a little bit above 0.5. 4 tails, you can kind of see. It doesn't matter how many of the previous coin flips came up tails, the probability I see a heads on the current coin flip is always right around 0.5, right? I mean, it is exactly 0.5, but we just don't have an infinite sample size here, so it's going to be a little bit off. So there's this really famous example, and maybe it can save you some money if you I don't know, ever step foot in a casino. But in 1913, there's a casino, and at the roulette table, you know, I know there's I don't know the technical term, there's a green space on there, so it's not technically 50-50, but for the sake of the example, think about it as 50-50, right? There's equal number of black, equal number of red spaces, and so I want to know, you know, what's the probability if I spin this wheel that it comes up black, right? Well, it's about 0.5, it's just like the coin flip example. But it just so happened that black came up 26 times in a row, right? So this is statistically very unlikely. In fact, I mentioned this a little bit last class, but if I've got several, like what's the probability it came up black on the first spin, second, third, it would actually be 0.5 to the 26 times itself 26 times, right? So I don't know what this is. Maybe we can take a look here in Excel in a second, but this is like 0, right? This is a very unlikely event, but it happened. What do you think probably happened around 8 or 9 spins when black kept coming up? Well, then so let's say the first 9 spins all come up black. On the 10th spin, what do you think people started to kind of put money on? Right. They started to think there's no way it can go 10 times in a row, right? But it doesn't matter what the first 9 spins were. The 10th spin is still probably 0.5. Well, if people are over betting on one of the on the other outcome, and then it continues to not go up, right? The casino made a ton of money, right? So you can imagine, like after the 15th time, nobody was betting, you know, putting money on red, but then it came up black again. So the casino won a bunch of money on that. So, you know, people falling victim to this gambler's fallacy can make companies a lot of money. In fact, a more recent relevant example. I know for a fact that this happens. Like they're getting really good. If you know what you're looking for, these online sports betting apps are preying on people's like falling victim to this, right? So they know that, you know, if someone scores 50 points in the previous game, people are more likely to bet that player scores the over or however many points they set it at, right? And so gambling companies like really kind of exploit the fact that they know their consumers often are going to fall victim to this gambler's fallacy. That player's probability of scoring 50 points again is exactly whatever it was before, right? With, you know, for accounting for other factors. So kind of a fun example. We'll do one more example, and I'll let you guys get out of here. So just, I guess we'll kind of see what people are thinking, and we'll use this to be our eye clicker for the day. So let's say, you know, this class, right, that I've got,
the question is whether or not, right? I assume I don't have any twins and every day is equally as likely for someone to be born on. What's the probability in a class this size that we would see two people have the exact same birthday, right? So just kind of put, this is a preference one. There's no right or wrong answer. It's just me getting a recorded response from you. So a class this size, and I think the numbers I use is 40 here in a second. That's not specific to every class, like my general class sizes. Which of these you think the probability that people have the same birthday, at least two people have the same birthday in the class? All right. Everybody got an answer? Like I said, no correct answer. We're just kind of getting preferences here. 24 of us. 25. Everybody got the response. I'm going to close it out. All right. So let's see what people are thinking. So relatively low, right, is what most people would think. So it's kind of interesting. If we go through this, right, we can always write an event as 1 minus its complement, right? So if we think about the event X being that two people have the same birthday, X complement would be what? Nobody has the same birthday, right? So we're going to solve for the probability of what we're interested in, right? That two people have the same birthday by 1 minus its complement. So how can I find the probability that nobody has the same birthday, right? Well, for the very first person I look at, like let's say I start here, the probability that he has a unique birthday is guaranteed, right? No, I haven't looked at any other person yet, right? So for the first person, the probability they have a unique birthday is 365 out of 365. When I go to the second person, well, now for them to have a unique birthday, there's only 364 possible days left that would give them a unique birthday. And then the third person, now there's only 363 out of 365. You could go through and do this for all 40 people, right? And then, okay, what's the probability the first person has a unique birthday, and the second, and the third? You'd just be taking each one of these probabilities and multiplying them by each other, right? So if you do that, whoops, did I not put the answer in here? Oh, no, hold on. I had it on this other one. I think I didn't copy and paste all of them. Here we go. All right. So if you do this in a class size of 40, what you end up finding is probably that everyone has a unique birthday. There's only about 0.1. Subtract that from 1. You get the probability that someone has a unique birthday. Or sorry, you get the probability that someone has the same birthday. At least two people have the same birthday is as high as almost 90%. Right? I don't think like you would think that, but kind of just with what we talked about with the complement rule, the idea of independent events, assuming everyone's birth was independent, no one's parents were trying to have kids at the same time because they're friends or something. You get that probability is about 90% in the class size of 40. Right? In fact, for it to be a 50-50, I think you only need 23 people. So as long as you get 23 people in a room together, the probability that two people have the same birthday actually becomes higher than the probability that everybody has a unique birthday. So kind of fun, just stupid, I guess, example. We'll end it there. I'll get that next Excel assignment out over the weekend. Parts of it will be some stuff we do later on as well. But at least we can take this table apart even to start on. Okay.
It would be great.